Okay. All right. Welcome in. I think we're good. Sorry, I was getting a text from my department head at the same time class was starting. So I think we're good here. Okay. Let's see. What do we got? Okay. Before we get started, are there questions? Does anybody have a question that they would like answered? Any concerns about the class and how things are going? I see people doing homework. Almost every student is making progress. Couple people skip the order of operations in the beginning. You might want to go back and get those. That's some points for you that you could grab here. But I'm not seeing questions. If you have questions, feel free to throw them into chat, and then we can definitely talk about it. But looks like, I guess, from what I'm seeing, I'm not getting questions, and I'm seeing people completing homework. Some of you have 100% all the way through simplifying expressions. That's great. Some people even are getting a jump on the solving linear equations, which is a lot of what I'm going to talk about today. And then just keep up the good work. I'll get a few more assignments up. Let's see. You're probably good for now. Monday, I'll put more assignments up to stay ahead of everyone so that you always have stuff you can be working on. And we will go from there. Okay? Okay. Well, then, if there are no questions about the course, we will move ahead and we will get into the actual, what we want to talk about today. So the next topic that I think we need to spend time on is solving equations. Now, this is specifically solving linear equations, but the truth is the tools that we use for solving these linear equations, you're going to use in the more complicated equations that we're going to be using down the road as well. So what I mean by that is, like, for instance, later when we learn the quadratic formula, which you'll actually learn next semester in Math 3, you learn the quadratic formula. The quadratic formula only works for second-degree polynomials, right? That's the only time you can apply that tool. But the tools that we're going to look at today for solving these linear equations, you will be using those tools in every type of equation that you solve. So sometimes it's a little misleading because they say, this is solving linear equations. And you go, okay, that's true. We are using these tools to solve linear equations, but also I can use those tools to solve any type of equation that I run across. You might need more tools than just those that we're going to look at today, but you will need at least those. So sometimes people call it solving linear equations, sometimes just solving equations, because these, like I say, the tools that you learn here, you will be using for the rest of your math classes, right? Any math class you take, you're going to be using these things that I'm talking about today. And that is, what are we really trying to do when we solve an equation? Well, this is left over from last time. Let's get rid of that. What are we doing when we solve an equation? Well, you're trying to put it into a form that you understand the information that is in that equation. So for instance, let's take this equation. So if I have 2x equals x plus 2. Okay, so when I first give you that equation and I say, okay, everyone, quick, tell me what's the solution here. What is x equal to? And you might go, I don't know. I can't tell by looking at it. I would have to solve it first, right? Well, when we solve it, we've gotten to a point where we know exactly what the value is. And what we've really done is we've written the equation in a different way where it presents us the information easily. So take the solved version, x equals 2. Okay, these two equations that you're looking at are mathematically equivalent. What does that mean? It means that they look different, but they encoded in that equation is the exact same information. They are equivalent. These equations hold the same information. But when it's in this first line, it's hard to see what the information is that it's encoded in there, right? I could give you a very jumbled up equation and say, try to solve this. And by looking at it, you're going to go, I don't know. I can't do that in my head. But down here, see the second version? This is still an equation, right? X equals 2. That's still an equation, but it's in such a simple form that we automatically know all the information we need to know. What do we know? I know that x is equal to 2. That's it. That's all there is. That's all the information. X has to be equal to 2. Okay? And that's the same thing up here in the first equation. If you plug in 2 for x, you get 4 equals 4, which means this equation encodes the information that x equals 2, but it does it in a much less obvious way, a much less helpful way, because I don't know what the solution is. So what I have to do is figure out the solution. So the question that we're going to tackle today is, how do I take something confusing like I see here in line 1 and end up with something simple and straightforward like I have here in line 2? How do I get from this first line to the second line? That's what we want to know today. Okay, so we have a couple of tools for doing this. And when you look in the algebra books, they usually have a picture of like a scales, like a balance, where you're doing the same thing on both sides. I think I talked a little bit about this last time, but I want to sort of expand to make sure we're going and you know, really going through it, because it's kind of looks to be where most people are in the class right now, is about to start this assignment. And it's really, really pivotal information that we need. So I want to make sure that we're going for it. And let me just double check. I have stuff. Yep, chapter 2 is released. So you should be able to go in and do those things. Okay, good. Just double checking. So we have a rule. Let's go to a new page here. We have a rule that says that we can add or subtract the same thing from both sides of an equation. And this makes sense, like the balance. If it's balanced, I have weights on both sides, and those weights may look different. I may have a 5 kilogram weight on one side and 5 1 kilogram weights on the other side, but the balance is going to balance, right? Well, if it's balanced and I add another kilogram to both sides, it should still be balanced, right? Or if I go to both sides and I take 1 kilogram away, it should still be balanced. Well, that's kind of analogous to what we're doing here. When the equation is balanced, that's what the equation, the equal sign is saying, is it's saying the value on the left is the same as the value on the right, then we should be able to add the same thing to both sides or subtract the same thing from both sides, and it still works. And we want to be careful. That's a very specific way of thinking about the problem. A lot of times if I ask people, what does that equal sign tell us? And they say, oh, it means the left and right are the same. And I could say, well, does it mean the left and right are the same? Because I see a variable on the left, but I see no variable on the right. Well, that's a difference. I see a 2, a number on the right, and I see no numbers on the left. So is it really proper to say that the left and right are the same? I would say that it's lazy and sloppy to say that. What we really want to say is that the value on the left is the same as the value on the right. The value of x is the same as the value of 2. And I know a lot of times people might say, well, aren't you just being picky? Why are you getting hung up on this little detail in the way of speaking? And the answer is, in mathematics, a lot of times when we're lazy with the way we say things, it leads to people actually making mistakes, right? I think I talked about this last time. The biggest way I see this is people come to me when they're doing adding and subtracting, and they go, oh, well, I learned that a negative and a negative makes a positive. No, what you learned is a negative times a negative makes a positive. So see how that laziness in our speech translates to a misunderstanding in the mathematics? So it's not just that I want you to say things a certain way, it's that I want you to understand things in a certain way. So that's why, it actually is important when we specify this. We're not just trying to make it a pain and unpleasant for people taking mathematics. It's because it makes a difference, and I see students lose points because they're not being careful with the way they say things. Okay, so let's start off. Let's go to another example. Let's say I've got 4x equals 3, 4x plus 2 equals 3x minus 7. Whoops, and it's not in math form. Okay, so 4x plus 2 equals 3x minus 7. So how can we use this to simplify things? Keeping in mind, one of the things we're going to be doing is combining like terms. We talked about that last time. I look in this equation and I see some like terms. I see some terms that have an x variable. I see some terms that have a constant. How am I going to get things together so it looks like an equation that's in the simplest form we can come up with? So, basically, what you want to think of first is I want to get all my variable terms on one side of the equation, and I want to get all of my non-variable terms on the other side of the equation. And it actually, in fact, I'm going to do it both ways. I'll show you it doesn't really matter. Either choice you make is going to get you to the right answer. So you could say, I want all my variables on the left. Like we could assign half the class. Half of you put your variables on the left. Half of you put your variables on the right. It's okay. It doesn't matter. But the goal is to get the unlike terms separated on different sides of the equal sign. So the simplest way to do this is to say, okay, well, if I have a rule that says I'm allowed to subtract the same thing from both sides of the equation, then why don't I subtract 3x from both sides? So I'm going to go through, I'm going to subtract 3x from both sides of my equation. Well, what do we have here? 4x minus 3x is just going to give us 1x, right? So let's talk about that. 4x minus 3x would give me 1x, but we don't really write it that way. I see some students writing it as 1x, and that's kind of okay when you're first learning how to go through and do this. But we want to get out of that habit, because what happens is when students write it as 1x, then when they're presented with a problem that just says x, they go, well, how many x's is that? I don't know. There's no number in front. So you want to recognize that the way we usually represent 1x is just by writing x. So see how it'll update in just a second here. See how it just says x? That means 1 times x, or 1x. If I have 4 x's and I lose 3 x's, I have 1x left. I just have an x, right? That 1x there. So 4x minus 3x is x, and then the 2 is not a like term, so it just stays plus 2 equals, and now on this side I have minus 7. So I just took care of subtracting the 3x from both sides. Okay. Now I'm going to go through and add 2 to both sides. Okay. So, I'm going to subtract 2. Basically, you're going to do whatever undoes the operation that's there. So looking at this problem, how do I know what the step is I'm doing next? Well, notice how on the left I have a variable and a constant, and I said I wanted my variables on the left. That informs me that I need to get my constants, the things that are not variables, on the right. So the offending term is this one, the plus 2. So how do I undo a plus 2? Well, to undo a plus 2, you subtract 2. So now I'm going to subtract 2 from both sides of this equation. And when I do that on the left, I just get x. That was the whole point of me subtracting 2. And then when I have negative 7 minus 2, I get negative 9. Okay? So if I did it right, that's our answer. Should be negative 9. So all I did here was I used the same tool twice. I used one time to subtract the variable term from both sides of the equations, and I did it once to subtract a constant from both sides of the equations, and I got my answer of negative 9. Now, how do I know I got the answer right? Because if I made a mistake, I'm still going to get a number at the end, right? I still would get x equals some number, but that number could be totally wrong. And when you go to put that number into Delta Math, you're going to lose a point when you get it wrong, and then you're going to have to do 2 problems in order to get back ahead, right? So it's worth my time to check it before I put it into the computer. And the reality is, it's not just I actually like that Delta Math does this, because in the real world, you have to check your answers too. Because if you're at your job and you have to run some math to figure out part of how your company should run, and you make a miscalculation, then guess what's going to happen? Your business is going to make a bad decision, right? It's not like your manager is going to come in and say, oh, we caught your mistake. We fixed it before it caused a problem. If you're doing work and you do it wrong, it's probably going to cause problems. So we need to check this problem, right? Not only because we want Delta Math to give us our point, but also because this is just what you have to do in life. You have to check your work. The good news is checking our solution is generally easier than finding the solution, okay? So if you solve an equation, especially, especially here shortly when we get to the more complicated problems that we're going to be looking at, solving an equation is much more difficult usually than checking a solution. So here it's going to be about the same amount of work because we're dealing with a very simple, I got the hiccups. We're dealing with a very simple problem. But when you get to a more complicated problem, it's way easier to check your work than to actually like solve it again. So all you have to do is remember, what is a solution to an equation? It's a number that when I take it and plug it into the original version, gives me a true statement. So let's see if this gives us a true statement when we check it. So if I plug in -9 and I take the original equation, I get 4 times -9 plus 2 equals 3 times -9 minus 7. Right? So see how it's like that evaluate that you did on some of your homework? I'm just substituting -9 in for x because that's what we think the solution is. So let's see. What is that going to give me on the left? So that gives me -36 plus 2 would be -34. And then on the right, I get what? 3 times -9 is -27, minus 7 is -34. And look, in fact, we do get a true statement. When I plugged it in, -34 is equal to -34, so we know 100% we did that problem right. See how it wasn't very hard to check? That's certainly better than doing 2 problems on Delta Math to get back, to where you wanted to do. So, this way, if you check it, you're just doing a quick check on the problem you already did. You're not having to redo entirely new problems. So that's how we check them, and that's how we use what's oftentimes called the addition rule, which says I can add the same thing to both sides of the equation. I can subtract the same thing from both sides of the equation. Let me get my book here. I didn't have this open, but let me open this so I can find some good problems for us to go over. Here we go. Okay, now the reason that this problem came out pretty simple is because when I subtracted the variables, we were just left with 1x. But what happens if you get to a point where you're left with like 5x equals 35? Then what are you supposed to do? Well, we have a similar rule to the one that says we can add or subtract the same thing from both sides of the equation, which makes sense if you think about it in terms of the scale. If I add 1 kilogram to both sides of a balanced scale, it's still going to be balanced, right? Okay, well, what about multiplication? Do we have a thing we can do with multiplication on our equations? And the answer is yes. Because let's say I have the balance and it's balanced, and I have, a 5 kilogram weight on one side and 5 1 kilogram weights on the other side. It's balanced. Even though they look different, it's balanced, right? Well, what if I double the weight on both sides? Will it be balanced? Yeah, it'll still be balanced, right? So we have this rule now that says we can multiply both sides of the equation by the same thing, or we can divide both sides of the equation by the same thing. Now, we can't multiply or divide both sides of the equation by 0. You can't ever do that. You can't divide by 0 anytime. And you don't want to multiply by 0 because that's essentially like just erasing all the information in your equation. So neither one of those is helpful. As long as you take a non-zero value, you can multiply or divide both sides of the equation by the same thing. So, sorry, just lost my train of thought for a second. Oh, right. So we could say double both sides of the balance. That would be fine. We could halve both sides. We could take half the weight away from both sides. It would still balance. That's what we're doing with an equal sign. Okay, so for example, let's get to a more complicated problem where I have to use the multiplication property. We'll start off with a simple one. How about this? 2x equals 8. Okay, we want to solve 2x equals 8. So what am I supposed to do? Well, I can't really add or subtract anything from both sides of the equation. The tool we just used a moment ago about adding and subtracting, that one's not going to help me here, is it? Because these are not like terms. So adding and subtracting isn't going to do any good. So maybe we want to use this multiplication / division rule that we just looked at that says I can divide both sides of the equation by the same thing. So why don't I divide both sides by 2? Why am I dividing both sides by 2? How did I know to do that? Well, remember our goal is always to isolate the x. We want to get to where we have x equals and then some number. Well, if I have 2x equals, then I have to get that x by itself. You're undoing whatever is done to the x. So remember up here, our x was having 2 added to it right here. So what did I do? I subtracted 2 to undo that operation. Well, it's the same thing down here. Here my x is being multiplied by 2. So how am I going to undo a multiplication by 2? I'm going to divide by 2, right? So if I divide both sides by 2, I get x equals 4. And this one you can kind of just check in your head, right? Just go, okay, what if I plug in 4? 2 times 4 is 8. Yeah, that works. So this was a real basic problem, but we can see how it uses that multiplication rule. Most of the time, you're going to have to use both. For most linear equation problems, you have to use both the addition rule and the multiplication rule, okay? So, yeah, we want to use the addition rule and we want to use the multiplication rule. You generally want to use the addition rule first. Technically, you can do it either way, but if you use the multiplication rule first, you're likely to create more steps for yourself. And what you're also going to do is create fractions where you don't necessarily need any fractions, right? So usually in problems, like we want to be prepared for when fractions show up in the problem. But when they do show up, I want to know how to deal with them. But they're kind of a pain, and so it's nice to avoid them. So don't introduce fractions if you don't have to. So do all your additions and subtractions first, then do your multiplications. And how do you know when you're done doing your additions and subtractions? Well, basically, you'll be at the point where your variable term is on one side, your constant term is on the other side, right? So let's get a little more complicated. Okay, let's do this one. Let's go down here. Okay, this might look way more complicated than the problems we've done so far, and actually it is, but it's not that much harder. Once you know the steps that you're supposed to go through, it's not really, like if you could do the ones a minute ago, you can do this one. So step 1, and I'll write out these steps. So write this out. Step 1 is to simplify both sides. Okay, simplify both sides. Let me go ahead and move this over. Can make this a little bigger. Still move that over. Okay, I'm going to simplify both sides. So remember what this means. We've been doing that. Let's go right there. You've been simplifying on your homework, and I just checked. Many of you, most of you in the class, have completed that simplify homework with 100%. That's great. Keep doing that. Simplify both sides. Well, let's look at the left side. Well, there's 3 terms over here. 2 of them are variable terms with the variable x, and 1 of them is a constant. So that means I can combine like terms over there, right? Well, that's what I want to do. So 4x minus 2x equals 4x minus 2x is 2x's, right? 2x. If I have 4x's and you take 2 from me, I have 2 x's left. So 2x, and then I've got that minus 7. So all I've done so far is simplified the left side of the equation. Now I'm going to simplify the right side. So now I see 3 terms, but 2 of them are constants, and 1 of them is a variable. Well, let's combine those constants. 1 plus 8 is 9, so the right side should be 2x plus 9, right? 2x plus 9. Okay. Oh, wait a minute. Oh, I'm sorry. I was reading my problem wrong. This is not right, is it? 4x, I was saying 4x minus 2x, but this is plus 2x, right? I can see this is going to be a problem. So this should have actually, this side on the left should actually be 6x. Sorry if I confused anybody. 4x plus 2x is 6x. I don't know why I was thinking it was a negative in my head. Maybe because I was talking about the previous problem where we subtracted 2. Okay, does everyone see that? If you have a question about what I just did, if I confused you, please throw it into chat so I can explain further. But hopefully everyone sees I just made a mistake. 4x plus 2x is 6x, if we're good with that. Okay, so now notice that my left side is fully simplified. So if it's 6x minus 7, those are not like terms. And on the right, 2x plus 9, those are not like terms. So there's no more real work I can do here as far as step 1, simplifying both sides. We just did step 1. We're good. Okay, so now I'm going to go to step 2. So step 2 is use the addition rule . Use the addition rule. And how do we know when we're done with that addition rule or what our goal is for the addition rule? Think of it this way. Variables on one side, constants on the other. Okay, so that's our goal with the addition rule. I'm going to get my variables on one side. I'm going to get my constants on the other side. So I just start looking at it. Well, what do I need to do in order to get variables on one side and constants on the other? Well, let's subtract the x's. I'm going to get the x's on the left. Don't have to do it that way. If you want to get x's on the right, be my guest. But in this case, I'm going to put the x's on the left. So I'm going to subtract 2x from both sides. And that's going to give me 4x minus 7 equals 9. Okay, so we're halfway there. I've got all my variables on one side, but I still have to get all my constants on the other. So I have 4x minus 7. How do I undo that minus 7? I undo it with a plus 7. So I'm going to add 7 to both sides. And by doing so gives me 4x equals 16. See, 9 plus 7 is 16. Okay, so 4x equals 16. Now we're done. We can't do any more of the addition rule. How do I know that? Well, look, I've got my constants on one side, my variables on the other. We've achieved the goal of step 2. We got there. So now it's time to move to step 3. And step 3 is to use the multiplication rule. We're going to use the multiplication rule, and usually this is like one step and done most of the time. Okay? So what do? Well, I've got 4x equals 16. My x is being multiplied by a 4. How are we going to undo it? Divide by 4. Divide by 4. So dividing by 4, I get x equals 4. Oops, wrong line. Uh-oh. What did I just do? There we go. X equals 4. And I want to know, is that right? Maybe I made a mistake, right? Like I actually remember, so see how I started off this problem with a mistake and then I happened to catch it, or was that, yeah. I started off this problem with a mistake and then I caught it. Well, if I hadn't caught that mistake, I'd still get a number down here. That would still be, I would still get something, but it would be wrong. It would be the wrong number. So let's take that original equation and let's plug our value in and see if it makes sense. So by doing that, I'm going to get 4 times 4 minus 7 plus 2 times 4 equals 1 plus 2 times 4 plus 8. So all I'm doing, everywhere there's an x in the original equation, I'm putting a 4 there. That's all I've done. I've changed the x's into 4s. And let's see, what does that give me on the left? That's going to give me 16 minus 7 plus 8, which is really going to be, what, 17 in a minute when we do that? And then on the right, I get what? 1 plus 8 plus 8. And simplifying both of those on both sides, I get 17 equals 17, which is true, so we know we did it right. I know that I didn't mess that problem up. Okay, so then we know we're correct. I can go put x equals 4 into my Delta Math homework, and I know it's not gonna, I'm not gonna lose a point because I already checked it. I know it's right. Okay, so that's the basics for solving those linear equations. You're going to be doing this all the time, even in advanced algebra, calculus, all those classes, statistics. You're going to be adding the same thing to both sides of an equation. You're going to be dividing both sides of the equation by the same thing. That happens all the time. Here's one that throws people a little bit. What if you're doing some work and you get down to this one? What if I get down to negative x equals 5? I see people get confused about this. There's actually a couple ways you could do it. Oops, where's my answer? Here we go. Negative x equals 5. Well, that's not our final answer. Sometimes people will go and they'll put 5 in as their answer, and then Delta Math says, nope, the answer is not 5. Well, that makes sense. Just plug 5 into this equation. You'd get negative 5 equals positive 5. That's not true. So 5 can't be a solution. That's because you didn't really solve for x, right? What did you solve for? You solved for negative x, right? You solved for negative x. And so with negative x equals 5, what's going to happen here is that we need to get x by itself. So how would I turn that negative x into a positive x? Well, the answer is you can multiply both sides of the equation by negative 1. And then when I say that, I oftentimes have a student say, oh, I learned that you're supposed to divide both sides of the equation by negative 1. It's the same thing, right? If I multiply both sides of this equation by negative 1 and you divide both sides of the equation by negative 1, we end up with the same answer. So effectively, it doesn't matter which one you do. So if I multiply both sides of this by negative 1, on the left I get an x, and on the right I get a negative 5, and we go, oh, that makes sense. X is equal to negative 5. Okay. And then you put negative 5 into Delta Math, and it tells you you're correct. So just look out for that. Sometimes I see students get to that point and then they get confused with the excuse me, with that value. Okay? With that part. Okay? So, where am I? Right. So there's that one. The other thing is you may have more complicated simplifying to do than I did right here. Like in this problem, we had some simplifying to do. You might also have distributive properties showing up in here. Remember we talked about distributive property last time? If there's a distributive property inside of your problem, just do it right at the beginning. Just do that distribution and then combine like terms. So that's why we did that work with simplifying expressions, because you're going to use it here in these equations. And there's other times you're going to use it too. But this is a good place to use them. Okay. Any questions so far? We're still doing good? Sorry, I look distracted. My department head keeps texting me, but I can't get back to her until after the till class, so she keeps texting me. Okay, so that's really what it comes down to for solving these equations. Sometimes you'll have more than one grouping symbol. We've been using the parentheses. Sometimes you have square brackets. You just treat those like parentheses. So don't let those scare you if you see them. Fractions and decimals, those will come up, right? So here's a convenient thing you can do. What is the best thing we could do if we ran across a problem that has fractions in it? And sometimes we have to deal with fractions. But sometimes we run across a problem with fractions and I go, you know what? I think maybe this problem would work without fractions in it. If only there was a way I could eliminate those fractions. And the good news is sometimes there is. Sometimes you can do that. So let's look, for example, at the following, because we can't be afraid of fractions in here. If you're gonna succeed in math, you got to have fractions. You got to be able to deal with those. And like I think I said this at the beginning of the semester, I find that most students are much better with fractions than they think they are. They just sort of are scared of fractions. Like they've had that, research shows that by the time people get to college, they've had probably at least one math teacher that they really didn't vibe with, right? It just wasn't working out. And a lot of times that one class, that one teacher is enough to really sour people on mathematics. And that's unfortunate because people are actually much better at mathematics than they think they are, or at fractions than they think they are. Okay, here's a great question. Could we convert them to decimals? The answer is sometimes. This is an excellent question. I'm glad this was asked in the chat there. Can we convert our fractions to decimals? Well, some fractions can be converted to decimals, and if you prefer to do it that way, go for it. We're actually going to do the same thing with decimals where we eliminate the decimals as well, right? But if you're someone if you find that you're comfortable with converting fractions to decimals, go ahead, but there's a problem with that, and it's a great question that was asked. So let me show you why. Let's say I take the fraction 1/4. And I want to convert that to a decimal. Well, hopefully you recognize that 1/4 written as a decimal is 0.25. Okay, that is a true statement. 0.25 is exactly equal to 1/4. That's fine. That works. That's good. Okay, so if you had 1/4 in a problem and you decided to write it out as 0.25 and move through the problem that way, that's fine. That's kind of the long way to do it, but it works and it would get you your answer. So that's fine. But we run into a problem here. What about the fraction 1/3? What if I have 1/3 in my problem? What is 1/3 equal to as a decimal? Well, it's equal to 0.3 repeating. That means it's a decimal and then 3's forever. Forever. Right? It never stops with the 3's. It's 0.3 repeating. So that makes it hard to do algebra with because I can't write an infinite number of 3's, right? Even this, where I wrote a whole bunch of 3's, that's actually still an approximation. It's a really, really good approximation, but it's still not the exact answer. In mathematics, we liked exact answers because if it's not an exact answer, it's a wrong answer, right? So we run into a problem here where we ask ourselves, well, like how many 3's do I need? And the answer is you need an infinite number of them, right? 0.3 is a bad approximation. 0.33 is a little better, but not great. So where do we cut that one off? So if you have like a 1/3 in your problem, you should not convert it to decimals because you can't convert 1/3 to a decimal, not properly, right? So in that case, the conversion to decimals isn't going to work. So what should I do? Let's see, how much time do I have? Okay. Let's say I've got the following. Let's do this. Okay, so let's say this is my equation. 1/2 x equals 1/8. Okay, darn, I got these fractions in there. How am I going to deal with that? Well, remember we have this rule that says I can multiply both sides of my equation by the same thing. So if we're clever, what should I multiply by? What should I multiply both sides of this equation by to make it simpler? Well, why don't we multiply by things that's going to make my denominators cancel? Because if your denominator in a fraction cancels out, you don't have a fraction anymore, right? Your numerator becomes the integer. So, I want to ask myself, is there a number I could multiply by that would make both of these fractions cancel out? That would make the denominators cancel out, and I would be left with integers. Well, let's see. What if I took 1/2 x and I multiplied it by 2? Well, 1/2 times 2 is 1, meaning I wouldn't have a fraction anymore. But if I multiply the right side, if I multiply 1/8 by 2, I then get a 4th. So if I multiply both sides of the equation by 2, that fixes one of my fractions, but it doesn't fix the other one. In this case, actually, it would solve the problem because I'm kind of giving you a simple one, but I'm trying to give you an idea of, this is more an example of how to get rid of those fractions. What if I multiplied both sides of the fraction by 8, or both sides of the equation by 8? Well, 1/8 times 8 is 1, so that fraction goes away. But what about on the right? What if I take 1/2 times 8? Is 1/2 times 8 a fraction? Well, 1/2 times 8 is 4. So basically what you do, in the most general sense, you look at your two denominators, or if you have 3 denominators, you look at all 3 of them. You look at all the denominators that you have available, and you multiply by the least common multiple, the smallest number that all of those divide into. So remember you did that work in your pre-algebra class where we looked at greatest common factors and least common multiples and all that kind of stuff? Here's one reason why you needed to know how to do that. Here, I want the least common multiple of 2 and 8. I want the smallest number that both 2 and 8 divide into evenly, and that number is 8. Okay, so I'm going to multiply both sides of this equation by 8, and that's going to give me 4x equals 1. 4x equals 1. And then what I'm going to do, what am I going to do? If you've been watching, you know what I'm going to do next. I'm going to use that multiplication rule to divide both sides by 4 and get that x equals the fraction 1/4. And let's check it. So in order to check it, we have to multiply fractions. Some of you may not have multiplied fractions in a while. Hopefully you did in chapter 1. You kind of remember how that works. But let's just remember. Let's see, I want to check this. So I'm going to have a fraction that is 1/2. Then I'm going to plug in my value for x, which is 1/4. And I want to know, what is that equal to? Well, remember for fractions, when you multiply, you're multiplying straight across. Right? You multiply straight across. That would give me the fraction 1/8. In fact, let me put a dot in here. That separation doesn't look very good. Let me see a multiplication sign here. There we go. That looks a little cleaner formatted. equals 1/8, and that's what it's supposed to equal, is 1/8. So yep, we found the right answer. We did it correctly. So you can multiply both sides of the equation by something that's going to get all your denominators to go away. Then you're left with an equation with no fractions. See how our second line has no fractions? And then we solve it. Now, we ended up with an answer that's a fraction. There's nothing you can do about that. If the answer is a fraction, you can't change what the answer is going to be. But see how we solved it without using fractions for part of the steps? That's a little cleaner. Great question was asked about decimals. Now, decimals are even a little bit more straightforward. Basically, we use a base 10 number system, so every place in a number is a power of 10. So if you want to move that decimal place, you multiply by 10. For instance, if you take 5 and you multiply by 10, what do you get? 50. If you take 50 times 10, you get 500. You're just moving that decimal place on the end of the number. So what you do is you multiply by a power of 10 that will move it the number of places that you need the problem to go. So let me write one in here. Let's do 0.2x plus 0.5 equals 0.2 equals 0.8. So I'm not even going to work through this problem because we're not going to have time. But what I'm going to do is tell you how to do this. So what you want to do is go through the problem and ask yourself, how many places do I need to move those decimal points so that I get rid of them? Whoops, this was supposed to be a point, not a negative, a 0.2x. Now, the truth is, if you didn't want to do this, if you wanted to do the problem and do all the fraction, addition, and subtraction in the previous problem, you could do it that way. And this problem, you could go through and you could do the problem by multiplying decimals and dividing decimals and that kind of stuff, and that would work out just fine. Okay, but it's more work. So it's kind of nice to put it in this simplest form. So what I'm going to do here is I'm going to look at my equation and ask myself, how many times do I need to move the decimal place so that all of my numbers are integers and not decimals anymore? Well, let's see. It looks like for each of these, I just have to move it one place. If I move the decimal point here, it would be 2. 2.0, or just 2 point, is like the number 0, right? All numbers kind of have a decimal at the end, but we don't write them that way. Like if it's an integer and the number 5, we don't usually write it as 5 decimal. We just call it 5. But to get to 2, I really want this to be 2 and with the decimal behind it. So I'd have to move it one place. Here I move it one place. Here I move it one place. So what can I multiply my equation by that will move all the decimals one place? Well, it's a base 10 number system, so we multiply everything by 10. When I do that, it tells me I have 2x plus 5 equals 8. Right? See, everything's multiplied by 10 now. If one of these decimals had been like 0.08, then we'd have to multiply everything by 100. That is 2 powers of 10 in order to move the decimal 2 places. You just keep moving them. And notice it moved all the decimals. You can't pick and choose. Sometimes people choose which values get multiplied by 10. We don't get to do that. We have to multiply everything by 10. And then you would just finish the problem from here on out the way that we did previously. Okay? So that should allow you to get through the solving equations part. Please let me know if you have questions, because I can start off our next meeting with some problems. If people have specific problems, you can send me a screenshot and I'll go over that particular problem, or just let me know there's a particular part of this lesson that you're confused about, and I can start off by answering those questions for you. Okay, we can go over them together. So try to do them by yourself, but if you get stuck, let me know and I'll address them at the beginning of our next meeting. All right? With that said, I'm going to shut down the YouTube stream, and then anyone who wants to talk to me is welcome to stick around in Zoom, or if you're on YouTube, you can hop into the Zoom meeting and talk to me, and I can clear things up for you before we go into the weekend. Okay, thanks everybody. We'll see you next